Welcome to Excel 2013 Statistical Analysis video number 58. Hey, if you want to download this workbook, this is 210 Chapter 9 second file. Click on the link below the video. Hey, we're still talking about the T distribution for hypothesis testing. Now in this one, we're going to do a one tail to the left. Now let's look at our example. Solid Construction is a company that builds decks for homes. The company recently employed a new building technique that is supposed to save time over the old method, which had a mean of 15.5 hours. Solid Construction's, boy, if only I could type. I'm glad you guys are tolerant. Solid Construction wants to determine if the new method actually saves time. A random sample was taken of the number of hours to build a deck. At the 0.05 significance level, can Solid Construction conclude that the new method is faster? All right, just like we've done in the 5 previous videos for hypothesis testing, we want to talk about point of view, what we're considering in goal. So the point of view is Solid Construction Company. They want to see if the new method is faster. We are considering the population of times for building a deck, and our goal is to run a hypothesis test to provide statistical evidence to determine whether the new method is faster than 15.5. All right, so faster than 15.5. Well, that means we want this new method to take less. So that means this is a one tail. The trick is you type your comparative operator less. It's pointing this way, so that means it's a one tail to the left. That little comparative operator that we just figured out from what is written here, or what we're thinking, leads us to go to the alternative hypothesis first. So we have alternative mu is space less than. All right, as soon as we know the comparative operator for the alternative, we jump up to the null hypothesis, and we do the opposite and add an equal sign. All right, so the old method had a mean time of 15.5 hours. So for both of these, we'll use that 15.5. Null, mu is greater than or equal to 15.5. Alternative, mu is less than 15.5. All right, our alpha, that's the risk of rejecting the null when it was true, 0.05. All right, let's come down here and do some calculations. Step 3. All right, sigma, we don't know that, NA. So in the test statistic, we are going to use T, not Z. All right, we'll go ahead and calculate. Here's our data over here. We'll calculate our standard deviation, STDEV.S. Control Shift down arrow, Shift Enter. So we have a standard deviation for the sample of about 4.5 hours. Sample size. We'll use count because we're counting numbers. Control Shift down arrow, Shift Enter. Degrees of freedom, we take our n and subtract 1 sample, 49. All right, our x bar equals average. Control Shift down arrow, Shift Enter. Shift Enter just jumps the cursor up. So we have a mean from this sample of 14.9. So it looks like in this sample, we certainly have a time less than our 15.5 from our previous method. Our alpha will equal our 0.05. Type of test. Well, this is a one tail to the left. We have to calculate our standard error. We don't have sigma, so we use S divided by the square root of our n. And then our ever important test statistic. This is the T distribution, so we're actually calculating a T. We take our sample error, x bar minus our hypothesized mean, divided by the standard deviation for the sampling distribution of x bar, standard error. So almost -1 standard deviation, right? 0.94. That's what that T statistic says. Let's look at a picture. So right-click, show. So there's our step 3. There's our hurdle line, our alpha, Anything on this side of the critical value will reject H sub 0 and accept H sub A. Anything to the right will fail to reject the null hypothesis. All right, so let's go ahead and calculate here's our test statistic, and we have two ways, either the p-value way, then we directly compare it to our alpha, or the critical value method where we calculate our critical value and compare it directly to the test statistic. All right, so alpha, when we're doing the lower end, it's easy. We just use our dist, so equals T dot dist. Our test statistic, our degrees of freedom, and this is cumulative 1. So we're going from negative infinity up to this z here, and it will tell us what the probability is. And so 0.17. We compare that directly to our alpha. Clearly, we're going to fail to reject. It looks like the method is not faster. Using our critical value, we use our T dot inverse, and we have our probability. Now, we want the marking point, the hurdle, so we slap in our alpha. And what's nice about the low end is you just negative infinity up to that point is exactly 0.05, comma, our degrees of freedom. So minus 1.67. So clearly, we can see that test statistic is bigger than this, meaning it's on this side. So let's look at a picture. Right-click Show. And there is our picture. If we're doing p-value, the p-value of getting minus 0.944 or less, that p-value is about 17.5%. Compare that directly to alpha. We fail to reject. Critical value, well, our test statistic is up here. It's not past the hurdle, so we fail to reject. Write our conclusion. Ever important, write our conclusion. Because our p-value is bigger than our alpha, we fail to reject. So because our test statistic is bigger, right? Minus 0.94 is bigger than minus 1.68. So because our test statistic is bigger than our critical value, we fail to reject. The sample evidence does not suggest that the new method for building decks is faster. Because we did get a sample of 14.9 hours, and that's less than our hypothesized mean of 15.5 hours, we may want to investigate further. Like maybe we want to try a larger sample. Now I went ahead and plotted this. As we mentioned in the last video, sometimes, I mean, here we just don't know. We have no population data for the new method. So sometimes the best we have is to plot our sample data. And maybe there's kind of a shape here. Looks like there's one way out here. Maybe we want to increase the n. Right? Try a larger sample. Also, another possibility here is investigate whether or not the techniques of the new method are being implemented properly. Right? So maybe there's this great new method, and it really should reduce the time, but we went out and ran this sample. It's not happening, so now we need to investigate further. So another way to say this is at a 0.05 significance level, our sample mean of 14.9 hours does not provide statistical evidence to support the idea that the new method reduces the time to build a new deck. Now, we do run the risk here. This is a type 2 error of not accepting the alternative hypothesis, meaning the method is faster when in fact it is or was. All right, that's our second example of T. This is a T-test on the lower. In our next video, we'll see a two-tail test for the T distribution. All right, see you next video.